Okay, so I'd like to thank the organizer, especially Professor Imbohe, and also the people at KAIST for inviting me here to speak. So my title is L-functions and the Langlands program, or maybe I gave the title like historical introduction to the Langlands program. Both are correct, but my emphasis will be on L-functions. What are L-functions? L-functions are generalizations of the famous Riemann zeta function. But before I get in there, let me start with the plan for today. So I'll start with some brief introduction, especially I'll say something about GUT in math. What is GUT? Well, it's grand unified theory. In Korean, they say 대통일 이론, but well, it sounds like a bit of exaggeration, but I'll say what that means and why it comes up, and then I'll talk about some histories, like history of L-functions and reciprocity, and then the Langlands program really began in 1967 with the letter of Langlands to the famous mathematician André Weil. So I'll talk about how it came about, and my primary example of the Langlands program, what it's saying or what it's trying to achieve, is going to be its application to Fermat's last theorem, FLT. And then at the end, I'll say something about what's happening now and possibly in the near future. Okay, so let me start. So here's Langlands. He's now quite old. He's like 81 or something. So he has a nice smile. But in any case, many of you may have heard of the Nobel Prize. It's intended to be the Nobel Prize in mathematics. We used to say we don't have any Nobel Prize in math. Maybe Fields medals are maybe the best approximation. But now, Fields medalists, to be a Fields medalist, you have to be under 40. But to win the Nobel Prize, it's really about lifetime achievement. So the goal is somewhat different. Fields medal is, in a sense, an encouragement to a young mathematician who made an impressive achievement. This is about lifetime achievement. I just quoted from New York Times article announcing this award this year, like a couple of months ago, and then the first sentence reads like this. In 1967, Langlands set out a roadmap to prove a grand unified theory that would tie together disparate areas of mathematics. So I'll explain what this means, just the first sentence. So what is grand unified theory? I'm not a physicist, but this is a notion coming from physics. And it's an attempt to unify three fundamental interactions in physics. You don't have to know what they are really. Electromagnetism, maybe you kind of know what it means, but weak forces, strong forces, it's not important, but the important thing is the following. To be accepted as a theory, or grand unified theory, or any theory in science really, there are some requirements to qualify. First of all, it should be consistent with known facts, or it should, there shouldn't be any contradiction, right? And but more importantly, maybe, theory has to make precise predictions and also new predictions. It's not enough to explain what's been known before. And then these new predictions should be verifiable or falsifiable, and then it should be confirmed by experiments. Then, you qualify. But as far as I know, no GUT has been successful yet, not completely. And there are some suggestions, of course. But of course, this talk not being about physics, I'll now say what it could mean by grand unified theory in mathematics. In particular, the Langlands program tries to achieve the following. So like there are three important themes in mathematics. I mean, this is not all of mathematics, so it sounds a little misleading when it says grand unified theory. It's not like everything in mathematics, but it's just about three important themes in math. There may be 100 or 1,000 important themes, but these are three important themes, especially matter to number theorists like me. And the first one, I mean, it's a kind of a very old problem, solving algebraic equations. Well, we've been doing this all the time, like in middle school, high school, solve a quadratic equation, find the root, Or, I mean, there could be like several variables. It gets complicated. And also you deal with functions all the time. But here, there are particular kinds of functions which have a lot of symmetries you're interested in. For instance, like the sine function, cosine function, these have symmetries because like you have like same pattern repeating itself, right? But there are more complicated functions with symmetries, and that's the subject of harmonic analysis. And another thing, well, we are interested in numbers, and well, when you try to extend the notion of numbers by attaching root of algebraic equations, then you get Galois theory. And Galois theory is really an important part of math, of course. And we like to tie these together. So that's what it means by grand unified theory in math, at least for the Langlands program. And well, and it does make precise and new predictions, as you will see. That's what the Langlands program does. And also, many predictions have been confirmed. And well, not everything has been proven, of course. I mean, we are quite far from it, but I mean, nothing has been really refuted. And also, it has been useful in the sense that it led to solutions of many important problems. For instance, Fermat's last theorem. And I'll talk about that more later in my talk. Are there any questions so far? So far, so good? Okay. Then let's get into something more mathematical now. Now, L-functions. So we'll see three kinds of L-functions. And you may have heard of the Riemann-Zeta function. If you haven't, that's fine. But then it will be a little difficult to digest. But and the Riemann-Zeta function has evolved in three different directions. First, Hecke L-functions. That's kind of in the direction of harmonic analysis. And the Artin L-functions, that's in the direction of Galois theory, and also in the algebraic geometric direction, the Hasse-Weil zeta functions. I'll define them, so don't worry if you haven't seen them already. Okay, so let me start with the outlook. Oh, there are many L-functions, right? Oh, so many. But well, it's like you just imagine you're looking at kind of evolution chart, right? I mean, there is maybe a few different animals, but then like over time, I mean, you have like maybe 100,000 different animals. But good news to you is that I mean, there are, in a sense, there are not 1,000 different kinds of L-functions after all. I mean, that will be actually one of the main points of the Langlands program, but at least just notice that there are three different directions. And I'll start my story from Riemann zeta and Dedekind zeta functions. Well, I mean, the letter zeta is a Greek letter. Hopefully you have seen. A little small, but it's small to recognize, but that's the Greek letter zeta. Okay, so what is the Riemann zeta function? Well, zeta function is given by this infinite sum of 1 over n to the s, where n runs over positive integers. And well, what do you think of when you learn about an infinite series? Does it converge, right? That's the first thing you learn in first course in analysis. Well, here actually I allow s to be not only a real number but a complex number. And as long as real part of S is greater than 1, you can show that it converges, absolutely. And well, actually it converges to a holomorphic function. With a little bit of complex analysis, you can show that. And well, you can also rewrite it as an infinite product over all primes P of these things. And then, well, if you don't worry about convergence, I mean, you can at least formally check that the infinite sum and infinite product are equal. Maybe I can, whoa, where is there a pointer? I thought there was, but I don't know. Maybe I forgot. Okay. Well, I mean, the infinite sum and infinite product are equal, but then, yeah, well, it disappeared mysteriously. And well, this infinite sum in the product can be rewritten as in this way. Well, that's a standard thing, right? As long as p to the negative s is, well, sufficiently small, you can do this. Okay, and well, in fact, the zeta function was first considered by Euler as early as in 1740. Riemann was more like a mid-19th century person. And it was generalized to Dedekind zeta function. Well, what is it? It's it came out much later. To do this, you have to allow some finite extension of the rational field Q. K is a finite extension of Q, a field extension. OK is the integral closure of Z. That is to say, I mean, it's you consider all kinds of monic polynomials with coefficients in Z, integral coefficients, monic polynomials. The highest degree has coefficient 1, and then you look at all possible solutions living inside K and attach them, generate a subring, and that's OK, the integral closure. So you have to think of OK as the extended notion of integers. Okay, so and you take an ideal, and the norm of A, and written n of A, is just the index of A in OK. It measures the size of an ideal. And then the Dedekind zeta function is pretty similar, but now you're summing over ideals, non-zero ideals, of 1 over norm of A to the S. And one thing you can think of is when K is Q, OK is just Z. So now you're looking at non-zero ideals in Z. Non-zero ideals in Z correspond to positive integers. And I mean, you can see that this is really a generalization. When K is Q, it just reduces to the above definition. Okay? And similarly as above, you can do this. Well, why is it true? Actually, it's not completely trivial. What you need is the unique factorization of an ideal into a product of prime ideals. That's something you learn in commutative algebra. But that's relatively elementary. OK is not a complicated ring, it's a Dedekind domain. Actually, Dedekind domain named after this Dedekind. OK, so what properties does it have? I mean, I said that these guys all converge in real part of S greater than 1. S is a complex number. But in fact, this can be defined for all complex numbers S. And in particular, it has at least 3 nice properties. One, Euler product. Euler product means it's a product over prime ideals or prime numbers of certain expression. It's an infinite product. And the reason why it's true is by unique factorization into prime ideals. And analytic continuation, well, this guy extends to all complex numbers, possibly with poles, but we know where the poles are. So I'll just say analytic, although there could be some poles. And functional equation just relates zeta of S to zeta of 1 minus S. So, well, the axis of symmetry is real part of S equal to 1/2. And if you heard of the Riemann hypothesis, then it says that all the zeros, non-trivial zeros, are on the axis of symmetry. But I'm not stating that, of course, because we don't know a single instance of Riemann hypothesis. So don't worry about that. that's not part of my talk, but at least you have the three properties. Okay. Are there questions? All right. Okay, so now maybe 50 years have passed. Now we are looking at Hecke L-functions. Still, you take this finite extension of Q, and I just recall how Dedekind zeta function was defined. Now what you do is, well, it gets a little technical, so I'll just say generalized class group, but I'll show you some examples later. If you don't want to think of what this is, then it's just a way to associate some non-zero complex number to each ideal A, but in some multiplicative way. Okay, so don't worry about the definition of generalized class group if you're not familiar. But it is multiplicative, and then you just form the same sum, but now you allow some flexibility. Numerator can now be some other number than 1. And that being multiplicative, you can actually get this product decomposition. It's the same game, really. Because each A is a product of product prime ideals in a unique way. And well, you can prove the same properties in this generality. And well, in this generality, it was done by Hecke in 1910s. And well, Euler product, analytic continuation, and functional equation. And it's good to keep in mind these three properties usually satisfied by nice L-functions. Okay. And well, maybe I can say that when K is equal to Q and you do this, then that way you get Dirichlet's L-functions. Well, what is it good for? Dirichlet L-functions are used to prove that there are infinitely many primes in an arithmetic progression. For that, you use some properties of this kind of L-function. Okay, and I say, well, just a technical remark, but Hecke L-functions in dimension 1, I said, well, there are two kinds of Hecke L-functions, really. In 1930s, Hecke associated L-functions with modular forms, if you know what modular forms are, and then that's kind of dimension 2 object. So that's why I say this one is in dimension 1. Okay. Okay, now we are in a different world. So far, Hecke L-functions have been in the direction of harmonic analysis. Now we are in the realm of Galois theory. So hopefully you have seen some Galois theory, but well, because we need this, we are going to consider L over K a Galois extension, a finite Galois extension, but possibly non-abelian. That's actually important. What that means is that the Galois group of L over K may be a non-abelian group. Well, and actually in math, we love non-abelian groups. Abelian groups are nice, but they're a little too simple. And a Galois representation really means just a representation of the Galois group. It's just a group homomorphism. It's a fancy name for a group homomorphism from the Galois group to general linear group of some finite dimensional vector space, right? GLV is really GLn of V if dimension of V is n, right? Just the invertible n by n matrices, they form a group. Okay, what did Artin do? Artin introduced a new L-function, and well, in 1923, and the definition looks a little complicated, but it's really linear algebra. I mean, you don't need anything much more. I mean, the only thing you need is this definition of this P, the Frobenius element. I could define it, but I mean, it's a slightly technical definition, so I'll just suppress that. But all you have to know is that P is a prime ideal belonging to K, and then there is a way to, well, attach an element of the Galois group. Really, it's actually a conjugate class, but well, never mind. I'll just write for P. And well, it looks horrible, but well, numerator is 1. That's okay. That's we can understand 1. Well, what is happening in the denominator is determinant of something, but if you really look carefully, then it's just the characteristic polynomial of rho for p. What is rho for p? It's just some element of GLV. That's just a matrix. And given a matrix, you can take a characteristic polynomial. And you evaluate the characteristic polynomial at this particular number, norm of p to the negative s. It sounds like a strange thing to do, but if you remember the definition of Hecke L-functions, Dedekind zeta functions, then that's a natural number you expect to see. So that when the dimension is equal to 1, it's exactly this. That really looks similar to the Hecke L-function I introduced before. Compare. You see? The same infinite product, but you just have, it comes with different coefficients. That's it. Okay, and then you wonder, well, given this, well, can they be related? Well, in a certain way. And that's exactly what Artin asked himself. Well, somehow he came up with this new definition of L-functions, and well, behind the scene, what's really happening is Artin was deeply influenced by Frobenius, who developed character theory, representation theory for non-abelian groups. And he used that to really motivate this definition. So character theory, really, a good amount of character theory goes into play. And that way, he could allow non-abelian Galois groups. That's actually very important. But even in dimension 1, when everything is abelian, because when dimension is 1, GLV is just the abelian group. So Galois group factored through abelian quotient. Well, and then in dimension 1 case, I mean, you have, well, somehow extremely similar definitions. And, well, and this curiosity drove him to prove his reciprocity law in 1927, just a few years later. Okay, I'll get back to this. But again, well, what are we interested in whenever we see an L-function? And these 3 properties are standard properties we ask of. And the Euler product, the interesting thing here is that by definition it's true. I mean, before it was an L-function was defined as an infinite sum, and you use unique factorization to show Euler product. Here, you defined it that way. So Euler product is just fine. It's just an infinite product over primes or prime ideals. Analytic continuation, still open. It's the famous Artin conjecture, still open, wide open. And in dimension 1 is fine, but in dimension 2, some cases are known. By the way, some case of this goes into the proof of Fermat's last theorem. That's called Langlands tunnel theorem. So it's actually important stuff. And the functional equation, it was proven by Brouwer in about 1950. And that uses character theory. That's part of representation theory. What you really need is the key input is the so-called Brouwer induction theorem. If you take a course in representation theory of finite groups, you learn about this. And actually, it was his motivation to prove this. I mean, that's why he developed that theory. OK? Yes?
How can I consider Frobenius experiment to LP Islamic one?
Yeah, great question. I wanted to hear that question. Because you can't. That's the shortest answer. And in fact, I mean, that he gave when P is reified, he didn't define the factor in 1923. And in 1930, in a later paper, he defined what the factor should be. Frobenius element is not defined, but what you can do is, I mean, you can tweak this a little bit, and well, gets a little technical, but roughly speaking, you have an inertia subgroup at that prime, and then if you take the invariant subspace of V by the inertia subgroup, then actually it factored through. I mean, the Frobenius image now makes sense, but I can give more detail later. But in fact, we have to make some adjustments at finite many reified primes. That's a great question. Are there anything else? Okay. Okay, Hasse-Weil zeta functions. So now we are moving away from Galois theory to go to L-direct geometry. But L-direct geometry over a number field, or maybe possibly over Q. For simplicity, I'll just work over Q. So if you don't know what a variety over Q means, then it's just a solution set given by a system of equations, algebraic equations, where coefficients are all rational numbers. There's a, let's say it has a smooth projective model over Z, but finitely many primes possibly removed. It's just bracket 1 over S means just a localization. So possibly away from finitely many primes. The Hasse-Weil zeta function is the product of a factor zeta p at each prime p. And what is the factor at p? Well, there's this horrible expression. It's some exponential of certain generating function. But what's important is, well, what it does is really counts the number of solutions. V of p to the r means you have an equation. V is given by a certain equation, and then you count the number of solutions in the finite field with p to the r elements. Then, well, the solution set has finite cardinality, so you can actually count and use that as a coefficient in rth place, and you just make some generating function. So whatever it is, it's supposed to encode number of solutions in each finite field. Okay, and that's all you care, and that's all it matters for my talk. And alternatively, I mean, you can write it in a way more similar to the previous definition. I mean, you can define the norm of a closed point if you're kind of more familiar with algebraic geometry, and then norm to the negative s. I mean, that's the kind of expression you've seen in other definitions. But if you're not familiar, that's just fine. It's supposed to encode number of points in each finite field. And what about the three properties? Well, Euler product, as in the case of Artin L-functions, is okay by definition. And in fact, I mean, this definition was, I think, influenced by Artin's definition, like defining an L-function as an infinite product rather than an infinite sum. And the continuation function equation wide open. Well, there are some instances where we know this, but in most cases we don't. Okay, so well, people often ask. I mean, non-mathematician friend often asks me, well, is there still a problem to solve in mathematics? Yes, the answer is yes. You've already seen many open problems. All right, so we've seen three different kinds of L-functions. The Hecke L-functions, Artin L-functions, Hasse-Weil zeta function. And the philosophy is, well, so after all, we know these properties only in the case of Hecke L-functions. That is kind of lives in the world of harmonic analysis. And basically, the philosophy here is that these three properties are relatively easy. It's not easy, but I mean, compared to the other cases, it's easier if L-functions come from analytic objects. That's the case for Hecke L-functions, but otherwise, they're almost impossible, just impossible. In the case of Artin and Hasse-Weil, we know very little. Okay. And if you have already forgot everything else, that's just fine. Just remember that there is this kind of philosophy. Okay, so now let me talk about something somewhat different, an early history of reciprocity. So there are some famous faces. If you recognize like more than three, well, this is Gauss, Hilbert, Artin, and Taniyama-Shimura. Okay, so we'll see their names pretty soon. So of course, I mean, Gauss did a lot of important work, but I'll just jump ahead to 1900. Gauss's quadratic reciprocity law was at around 1800, so it's about 100 years later. Well, Hilbert, ninth problem is basically this. I mean, he had 23 problems, but, well, ninth problem is to get a general reciprocity law. Generalizing the famous quadratic reciprocity law, which you may have seen in a first course in number theory. So here's an example of something more general than quadratic reciprocity. Well, one way to view quadratic reciprocity is you're trying to find the square root. Finding a square root modulo, let's say modulo prime. So you're solving an equation like x squared equals 3, modulo 5, modulo 7, things like that. But then from this viewpoint, you can ask a similar question for any other polynomial. Not just x squared is 3, but let's say this complicated equation, which really comes from a factorization of x to the q minus 1. It's an irreducible factor of xq minus 1, right? When q is a prime. So, and you ask whether the solution exists or not modulo p for some prime p. So it's the same type of question as in quadratic reciprocity. And well, let's see. Well, I'll just tell you the answer. I mean, you can run some experiment, but it turns out that it has a solution if and only if it has all possible solutions, q minus 1 solutions equal to the degree, if and only if p is actually 1 mod q. Well, that's a deep result, but I mean, from today's standard, it's not terribly difficult. And the main point is this, that you usually see in an undergraduate algebra course. Essentially follows from, well, not maybe this, but Frobenius elements are usually defined in a graduate number theory course, but well, it essentially follows from Galois theory of cyclotomic fields. Cyclotomic fields mean like some extension of Q you generate by roots of unity. And zeta Q means the primitive root, qth root of unity, primitive root of xq minus 1. And you attach this element and you generate a field, and then it turns out that it's a Galois extension. What is the Galois group? Galois group is isomorphic to Z mod QZ cross. Cross means the multiplicative subgroup of the ring Z mod QZ. And in a way that Frobenius elements at P, I didn't define them, but whatever it is, it corresponds to P. Well, so it looks so natural, and that's really a God-given isomorphism, so we call it a canonical isomorphism. And really one of the fundamental results in Galois theory. Okay. But then, well, I'll relate this back to the discussion of L-functions pretty soon. So it'll show up again. Okay. So let's go to 1920s. That was 1900 or earlier. Now I talk about class field theory. That's a great achievement in mathematics, especially number theory, in the early half of 20th century. And global class field theory was more or less completed in 1920s. And it gives a general reciprocity law, especially it can explain x squared equals q, or that equation I've shown you, and many more. So it gives you some general reciprocity, although it's not general enough. And more precisely what it does is the following. It classifies abelian extension of number fields. Number field means a finite extension of Q. Or if you like, just fix Q, and then you want to classify, you fix K, and then you try to classify all Galois extensions, or if you like, finite Galois extensions whose Galois group is abelian. Being abelian is a strict requirement, but for all abelian extensions, you can actually classify those extensions. And moreover, Artin reciprocity says something more precise, and it identifies the abelian Galois group with the generalized ideal class group. Okay, well, to be honest, I didn't quite define ideal class groups, but it's just some group generated by prime ideals modulo a certain relation, and in a way that Frobenius elements correspond to prime ideals. Prime ideals are elements of ideal class groups. These are generated by prime ideals, and then prime ideal is an element here. Frobenius is an element on the left-hand side. They correspond. So that's really a generalization of the canonical isomorphism for cyclotomic fields. Okay, and then moreover, more relevant to our discussion is the fact that Artin L-function is equal to Hecke L-function in dimension 1. So I briefly indicated that there is a similarity, but now we see that this is exactly true. And let me illustrate how this works in a special case of cyclotomic fields. So we've seen this isomorphism in a way that for every prime p, p on the left-hand side goes to fro p on the, well, p on the right-hand side goes to fro p on the left-hand side. So for concreteness, we now understand these groups. So what are Artin L-functions and Hecke L-functions in this case? Well, via this isomorphism, you can take a character. Character means just a group isomorphism. Character on the left-hand side and character on the right-hand side. Via this isomorphism, character on the left-hand side matches a character on the right-hand side. Right? And because fro p goes to p, when you match two characters via this isomorphism, then rho fro p is equal to chi of p. Right? Because, I mean, you get chi from rho by just composing with the isomorphism. So what this tells us about their associated L-functions, remember that L-functions are given by infinite products, Euler products. And then the Artin L-function in dimension 1 case was product of 1 over this number, and then Hecke L-function was that. But because the coefficients are equal at every prime, well, of course, going back to that question, well, in fact, you have to be careful about finitely many primes that are ramified in the extension, but let me ignore that issue. You can actually do this in the ramified case as well. Then, I mean, it tells you that L-functions are equal. Okay? So it follows as a consequence that L-functions arising in two different ways are actually the same. Okay, are there questions? But one thing to notice is that Artin actually defined an L-function for also non-abelian Galois groups, but here you can only explain abelian case. If the Artin L-function comes from an abelian Galois group, then you can identify it with Hecke L-functions. A natural question is, well, if you start with a non-abelian Galois group and genuinely non-abelian representation, there's still an L-function in Artin's world. What is the corresponding L-function on the other side? I mean, that's, and you'll see that the Langlands program actually gives you an answer, a conjectural answer. Okay? So here's what we want. Remember that Hilbert's ninth problem is to find the general reciprocity law. And we want to account for, as I said, non-abelian Galois groups, or like all representations of the Galois group. In fact, that's a kind of holy grail for algebraic number theorists. I mean, whatever it means, we like to understand the whole Galois group. Say, we have field of rational numbers Q, and Q bar is the Elliptic closure. Let's understand the Galois group, the full Galois group, Q bar over Q. And to do that, you have to understand all non-abelian Galois groups and their representations. And well, if you're coming from algebraic geometry over rational numbers, like finding rational solutions of algebraic equations with rational coefficients, things like that, that's a matter of algebraic varieties and you have associated Hasse-Weil zeta functions. Well, what are possible reciprocity laws accounting for this? So, well, for concreteness, I'll like to look into the case of elliptic curves now. Okay? And you'll see some non-abelianness in the Galois side, and you'll see something interesting happening in algebraic geometry. But for my talk, I'll just say elliptic curve for me means this equation, or a solution set thereof. Some quadratic equation in y, variable y on the left-hand side is equal to some cubic equation in x on the right-hand side. Okay. And coefficients are all integers. Well, the technical definition is a smooth projective curve of genus 1 over Q and with a marked rational point, or an abelian variety of dimension 1, but well, forget it. I'll just take this equation as the definition. Okay, and well, you may know that elliptic curves are quite famous. For instance, I mean, if you understand their solutions, rational solutions well enough, then you may win $1 million. That's basically the main point of Birch and Swinnerton-Dyer conjecture. By the way, the famous BSD conjecture is stated in terms of the L-function of an elliptic curve. So, well, to win $1 million, the first step is to understand L-functions of an elliptic curve, which I'll explain you in this talk. But before looking at rational solutions, let's look at, I mean, in case you're not familiar, what does the solution set look like over real numbers or complex numbers? For real numbers, you get a nice curve like this. And solution set over complex numbers, well, it's a curve over C of dimension 1, but curve over complex number really means if you visualize over real numbers, it has dimension 2, so you really see a surface. And it looks like a torus or donut or bagel, if you like. Okay, so, well, how do you define an L-function of an elliptic curve? Again, my standard strategy in my talk is I'll ignore finitely many primes where elliptic curves have bad reduction mod P. So if you're an expert, please forgive me. But I'll just say for every prime, but really, you have to do something else at finitely many primes with bad reduction. AP of E is defined to be P minus the number of solutions, modulo P. I mean, you have an equation. You can try to count the number of solutions mod P. In other words, you count the number of solutions in the finite field Fp. And you have two variables, x and y. So there are p possibilities for x, p possibilities for y. So there are p squared possibilities. That's the maximum possible number of solutions. But you just count those solutions that really satisfy the equation, modulo p. And that's a technical definition. And why do you do this? Why do you not take just the number of solutions, but p minus the number of solutions? There's an explanation, but I don't want to go into that. One way to think of it is, well, it's actually an Euler characteristic, h is 0 minus h1 plus h2 if you take homology of an elliptic curve, but never mind. And if you're an expert, you will also object that why is it p? It should be p plus 1, but well, that's because I'm taking an affine curve, not the projective version of the elliptic curve. So, okay, well, hopefully I'll satisfy experts in the room as well, like Professor Lim, for instance. So an example, well, I mean, it's really an elementary thing. If you want to just fix an elliptic curve equation and then fix a prime, you just count the number of mod 5 solutions. I mean, this is easy to do. So in particular, with with help from a computer, well, you can generate a huge database to try to understand these numbers. But the definition looks like this. Using these numbers as coefficients, you form an infinite product where still you have some numerator is always simple, but the denominator is now a quadratic polynomial in the variable p to the negative s. That's something you have seen also in the Artin's definition. Artin's definition was that you take a characteristic polynomial and evaluate the variable at p to the negative s. So it's a kind of similar pattern, but I mean, it looks somewhat different. But the precise technical background is well, probably it's better to skip, but just believe me, this is a good definition. But you may have noticed that its quadratic nature is something important. It's a quadratic polynomial in p to the negative s. So it actually has to do with some two-dimensional symmetries. And the reciprocity law in this context is, well, you want to understand these numbers AP of E that you have for each prime P. Well, let's say E is fixed, and then now you vary the prime P, and you have like infinitely many numbers for each prime P. Well, is there any meaning in these numbers? Or convenient to package the information is you just form an infinite product and then you get an L-function. And the reciprocity law asks, can you find the same pattern in a different part of mathematics, either in the form of an infinite sequence of numbers, or possibly just a single complex variable L-function? Okay, so that's a rephrase of the reciprocity law we are looking for. Okay. Now let's look at other kinds. Now, elliptic curves, they belong to algebraic geometry. Modular forms, more like harmonic analysis, more complex analysis a priori, because it's a holomorphic function. And modular form is given by, the precise definition is slightly complicated, but first of all, it's a holomorphic function. It's defined on the complex upper half plane in the variable z with lots of symmetries. Instead of writing down the exact equation expressing the symmetry, it's enough to understand that it just is lots of symmetries, kind of self-replicating in a way. That in particular, you see this gray area. That's the fundamental domain for the SL2Z action on the upper half plane by linear fractional transformation. And well, once you know the value of this function on the gray area, then you can copy yourself to get values on here and here and here and here, well, everywhere in the upper half plane. And in particular, you can jump by one to the left or to the right. Actually, one of the symmetries is that f of z is equal to f of z plus 1. That gives you a Fourier expansion of your function, and then actually that infinite series is the Fourier expansion. F of q is equal to some infinite series where q is e to the 2 pi I z, then well. But if you're unfamiliar, then just take that infinite series as a definition. That's fine. It's just you have some power series, and there are infinitely many coefficients, which are a priori complex numbers. But lots of symmetries mean that these coefficients cannot be arbitrary, but coefficients are strictly constrained. Only very special sequence of numbers can appear as coefficients. That's all that matters for my talk. So here are the points. Coefficients are constrained by symmetry requirements. And in fact, if you normalize it properly, in particular, if you require that, if you scale the functions in a way that the first coefficient is equal to 1, and actually here I'm talking about cost form, for experts. Then, well, actually, these are algebraic integers, not just arbitrary complex numbers. So now we are kind of closer to number theory, right? So something is really happening there, right? And if you have a modular form of, like eigenmodular form of weight 2, well, to define eigenform, I have to talk about Hecke operators, but never mind. Well, you have some nice modular form well chosen, and then there's some property. There's some basis of modular forms, if you like, in the space of all modular forms, then you can associate an L-function. It's, again, an infinite product. Well, there's a different way to do this. I mean, taking a Mellin transform, but let's say this is the definition for us. And the definition is that for each prime p, APF appears as a coefficient of p to the negative s, that's the degree 1 term, and then there's a similar degree 2 term here, quadratic term, in the variable p to the negative s. Okay. So this way, written this way, I mean, it looks terribly similar to the definition of L-functions of an elliptic curve, right? It's just that the only place where they differ is this place. Before I had this AP of E, now I have AP of F. They come from completely different sources. One, by counting number of solutions for a certain equation. Here, I'm just taking a coefficient of, or if you're familiar, actually this is also an eigenvalue of certain Hecke operator for the given modular form. Completely different, coming from completely different sources. But if you forget this definition for a moment, that's fine. One thing to remember, going back to our philosophy, this comes from an analytic object, and somehow it's easier to show, and it is indeed known that this L function has analytic continuation and functional equation. And Euler product, by definition, or if you take a different definition, then you can prove it. Okay? So we've seen L functions of elliptic curves and modular forms. Now I'll tell you what Taniyama and Shimura conjectured. Well, I believe they had kind of less complete information, but still, I mean, they were able to make a totally remarkable conjecture about elliptic curves and modular forms. And that's on reciprocity for elliptic curves. And it says the following, well, remember that these L functions were pretty similar, except that you had different numbers in some place of the definition. Now the conjecture says that these numbers are actually equal, or more precisely, given an elliptic curve, there is a corresponding modular form in a way that these numbers are all equal, not for some primes p, but for all primes p. And well, again, you have to do something for primes with, well, bad reduction or something, but again, I ignore that issue. It can be taken care of. And in fact, you can also think about a converse direction. Well, right? Whenever you see a statement in mathematics, if one says that, well, if you have something in A, then you have something in B, then you can always ask a question backward. So you can also ask, if there's a modular form, is there a corresponding elliptic curve? I mean, the question is yes or no, but well, basically this type of question has been settled actually pretty soon after this conjecture, maybe just a few years later, pretty much, by Eichler and Shimura. So really, the main conjecture is this direction. And as I said, it can be rephrased as the equality. Well, clearly this implies that, and to go backward, it's probably you need some more work, but never mind. Well, but formally, you see that this is also analogous to Artin reciprocity. Rho of rho p is equal to chi of p. You have seen this in the case of cyclotomic fields earlier in my talk. And well, that equality was used to precisely imply that Hecke L-function is equal to Artin L-function in dimension 1. And it plays a similar role here. And that's what's happening. And it was a conjecture. I mean, many of you probably know that now this is a theorem, but it was amazing at the time, and of course, not many people believed. Okay. But if you know this, then what's good? Well, one good thing is that because LSF has all these nice analytic properties, well, you can just carry over these properties. And now the L function of an elliptic curve has these properties. And there's no known proof proving this directly. The only way is you prove this equality, and therefore this is true. That's the only known proof. And of course, I mean, you need this to even state the Birch and Sri-Newton-Dyer conjecture correctly or unconditionally. So it's an important corollary if you prove the conjecture. Okay. And to formulate general reciprocity, well, by general I mean now I've been talking about the case of elliptic curves, and even that special case was so complicated. But if you want to go more general, then one thing that's clear is, well, you need some other kinds of L functions. You need a way to generate more L functions to account for other kinds of algebraic varieties, right? So for elliptic curves, modular forms were enough to explain them. But if you say consider other types of equations, then you need some other L functions, or like other kinds of L functions coming from maybe something more general than modular forms, so that you can see this kind of reciprocity. Okay. Oh, did I start at 4:15? Oh, it's already time. Okay. Well, that's a shame. Maybe I talked too much. Maybe I should get to. Well, at least I should tell you about Langlands. So maybe I can skip the later slides, but let me just maybe try to complete part 3 and possibly stop. And now we are in 1960s, 1967, Langlands' letter to Weil. And well, it was 17 pages long, but well, Langlands raised basically two main questions. First question and the other question, and it's about generalizing something. And it's really fun to read, but I'll skip that and just explain what were the main points. So Langlands proposed a huge new supply of L functions. I said that these were needed to make sense of or formulate more general reciprocity law. And he did this by starting from automorphic forms, which are generalizations of modular forms. And from automorphic forms, he gave a recipe for generating L functions and predicted that these have all these nice properties like analytic continuation, functional equation, etc. And these were verified, in fact, later. And the second question Langlands raised was general reciprocity law, indeed, and going beyond the abelian case, which was basically class field theory. So it's supposed to deal with all non-abelian reciprocity laws. And in particular, well, it will imply that L functions coming from Galois area algebraic geometry should be equal to L functions coming from automorphic forms in question 1. And the diagram shows you that, well, if the L functions defined by Artin and Hecke are like this, then Langlands' supply of L function is much bigger. And in fact, Artin and Hecke's territories would look infinitesimally small compared to Langlands. And well, where did it come from? I should skip. This is technically a part of the talk. It came from Eisenstein series. That's one, if I should say just one word. And maybe I'll explain the diagram and perhaps stop. I can tell you in person kind of more stories, but here's the diagram. Like before Langlands, it was like this. I mean, there were like 3 different kinds of L-functions: Hecke, Artin, and Hasse-Weil. Now, well, class field theory identified these when in the dimension 1 case. But then what Langlands is proposing in his program is the following. First, generalize Hecke's L-function. So huge generalization. So very general definition of L-functions. And then now what? Well, now his reciprocity tells you this. Well, Artin L-functions really fall into Langlands L-functions, which are generalized from Hecke's L-functions. And then Hasse-Weil's L-functions, they count number of solutions in algebraic equations in finite fields. These guys still give you the same L-functions. Of course, I mean, these are conjectures. And to be precise, I mean, this arrow was developed not in 1967, but a little later. But still, I mean, it's an amazing conjecture. Now 3 things are now identified through L-functions, and then, well, has great consequences, like Fermat's last theorem. And this way, in a way, it deserves the name grand unified theory. So, well, I was planning to give you some kind of more concrete example of what happened after that, like, for instance, in the case of Taniyama-Shimura conjecture and Wales's work, but because I'm already ran over time, I think this is a good place to stop. Thank you.